Okay. Hello, my name is John McClelland. I'm a master's student at Carleton University at the Creative Interactions Lab. I'll be presenting our paper, HaptoBend, Shape-Changing Passive Haptic Feedback in Virtual Reality. As an introduction, to HaptoBend, we describe it as a handheld shape-changing haptic device for virtual reality. It allows real-time tracking of shape and rotation that can be mapped to different virtual objects. So our motivation behind this is that we wanted to create a simple haptic device that would allow several shapes for haptic feedback. Using past research in visual dominance, we hoped that this would create an effective haptic system for a variety of objects. And so by combining past research in virtual reality haptics, shape-changing interfaces, and visual dominance, we arrived at our prototype, HaptoBend. Going into a bit more detail of each of these, we can see that virtual reality haptics have been seen to improve presence and task completion, as well as having specific benefits to selection and manipulation. Virtual reality haptics can be classified into two main categories: passive haptics, which rely on props to stand in for virtual objects, and we identified some problems with both of these. For passive, it was that many props need to be used for a more general system, and that switching out props can add complexity. For active haptics, these are used kind of actuation and force feedback for haptics, and they rely on, they can be intrusive, expensive, large, and immobile as kind of negatives for those. In relation to visual dominance, we see that past research shows that sight dominates our perception of virtual environments. This allows us to tolerate differences between what we see and the physical haptic feedback that we receive. As a result, disparities in size, shape, and weight can be overcome. Research in substitutional reality by Simeon et al. Shows a strong example of this. They ran two studies, one where they tested the effectiveness as a mug for passive haptic feedback on a variety of virtual objects that were similar but varied in different ways. They also looked at a variety of physical objects as proxies that were somewhat similar to a lightsaber. And overall, they found that disparities between the physical feedback and the virtual objects could be tolerated by users. And the third aspect, shape change. Shape-changing interfaces allow a device to translate between several physical shapes, either through actuation or deformation. They already make up an established research field, but have not seen very much application directly to virtual reality. To illustrate the effect of shape change we experience in everyday life, we can think of something like a newspaper. When we are reading a newspaper and it's laid flat, it's very much used in 2 dimensions, and it's flexible. However, if we roll the paper up to swat a fly, it becomes rigid, more 3-dimensional, and is used within 3 dimensions more. So combining virtual reality haptics, visual dominance, and shape-changing interfaces, we arrived at our HaptoBend prototype, which is able to deform into different shapes, allows creating a real-time digital model for use in virtual reality, and can also be mapped to virtual objects to provide haptic feedback. Here is an example of some of the shape-changing affordances enabled by HaptoBend. HaptoBend is composed of 4 main components: an IMU to measure yaw, pitch, and roll, 6 metal hinges that allow bending, 3 twist potentiometers to measure the bend angle, and 4 rigid sections connected by the hinges. To feed sensor information into our virtual environment, we used an Arduino Uno, which sends serial data to be captured in Unity. Within Unity, we created a simple virtual model of HaptoBend, which was then people were able to interact with while wearing an Oculus CV1. We tested HaptoBend in a user study with the goal of learning more about users' impressions, looking at what haptic shapes participants preferred for different virtual objects, and how HaptoBend performed overall as a haptic feedback device. We collected qualitative data by asking participants to familiarize themselves with HaptoBend at the beginning of the study and think aloud about their first impressions. At the end of the study, we also asked participants what their biggest observed negatives and positives were. The bulk of our study consisted of a haptic shape elicitation exercise. We based this off gesture elicitation studies first developed by Wabruck et al. While this original work was used to determine preferred gestures for different multi-touch functions, we co-opted to examine the most preferred haptic shapes for different virtual objects. By emulating follow-up questions by Wabruck et al., we can also look at the quality of haptic feedback provided by HaptoBend. Outlining the elicitation process further, for each virtual object, a participant would start with a virtual model of HaptoBend in a neutral state. We then introduced a virtual object co-located with HaptoBend. Participants were asked to create their most preferred shape for manipulating the virtual object. Once participants notified the researcher, or once participants had achieved their preferred shape, they notified the researcher. And then using a keystroke, the researcher would transfer the rotational tracking from HaptoBend to the virtual object. And at the same time, the virtual model of HaptoBend would disappear. This allowed participants to control the virtual object with HaptoBend as passive haptic feedback. Here's an example of what this would look like in the user study. Through the elicitation exercise, we were able to collect information for agreement scores, which measure the consensus of preferred shapes for each object, goodness ratings to measure how well or how satisfactory the haptic feedback was, and ease ratings to examine how easily participants could form their preferred shapes with HaptoBend. As a result, we had 3 dependent variables: preferred shape, goodness ratings, and ease ratings. We had used a 2x3 within subjects design with the objects that we used, which there were 6 of, divided by 2 categories. So we had 3 objects designated as 2D and 3 as 3D. 3D objects were flat, single plane objects that are normally used in a 2-dimensional context, while 3D objects consist of multiple intersecting planes and are commonly used in 3 dimensions. Objects were also classified as small, medium, or large, with medium being around the same size as the virtual model of HaptoBend. 20 people participated in our study from the ages of 21 to 38. 7 were female, 12 were male, and 1 was a no answer. This resulted in 120 of shape to virtual object mappings. Overall, our study resulted in positive user impressions of HaptoBend, agreement scores that varied in between virtual objects, and high goodness and ease ratings. At the beginning of the study, many participants were already thinking of objects that HaptoBend could act as a physical proxy for. The top positive attributes that were observed by participants was the responsiveness, mentioned by 10 people, affordances of bending, mentioned by 8, and the diversity of applications mentioned by 6 people. The most common negative attributes observed were the only having 3 hinges for bending, observed by 6 people, the inability to make complete 180-degree bends, which I'll reference later in the talk, mentioned by 5 people, and size difference with some virtual objects mentioned by 5 people. During the study, we observed 8 original shapes being used by participants for haptic feedback. Similarly to the virtual objects, we divided these into 2D shapes and 3D shapes. 2D are kind of defined if the intent of the participant was to create a single flat plane, and 3D was denoted to shapes where the intent was to bend the device into multiple intersecting planes. Here we can see the observed shapes in the 2D and 3D categories. In this graph, we see the usage of each shape for each virtual object. 2D shapes are shown in green, and 3D shapes are shown in purple. We see that 2D virtual objects have much higher prevalence for 2D objects, and 2D shapes are much more prevalently used together, and 3D with 3D as well. To calculate agreement scores, we used an updated method by Vadavu and Wabruck. The benefits for this include placing scores on a true 0 to 1 scale, with a 0 meaning that all participants had different preferences, and with 1 meaning they all shared the same preference. The scores are also more accurate and can be compared using Cochrane's Q. However, they result in lower scores than the original method. Graphing each object's agreement scores, we can see that the flashlight achieved the highest score, while the smartphone achieved the lowest. Comparing these shows that the smartphone was significantly lower than the notebook, the tablet, the pen, and the flashlight and the sledgehammer. Oh, sorry, not the pen, just the notebook, tablet, flashlight, and sledgehammer. The tablet was significantly lower than the flashlight, and the pen was significantly lower than the flashlight and the sledgehammer. To gather goodness ratings, we followed Wabruck et al. By asking participants to rate the statement, the shape I picked is a good match for its intended purpose, and they would rate that on a 7-point Likert scale. We compared this using Mann-Whitney-U. Here we can see goodness ratings summed for each shape mapped to the virtual objects. We compared these, and it showed that the pen was significantly lower than all other virtual objects. Overall, the ratings were quite high, with the flashlight and the sledgehammer receiving neutral or positive ratings exclusively. To gather ease ratings, we again followed Wabruck et al. By asking participants to rate the statement, the shape I chose was easy to perform, and rating that on a 7-point Likert scale. By graphing these ease ratings, some for each shape mapped to the virtual objects, we see very positive ratings. The only negative ratings that can be seen are shape A, mapped to the tablet, and shape G mapped to the pen. Using our results, we established several major findings. We found that shape change can be an effective approach to generalized passive haptics. Physical approximations can allow passive haptic feedback that's relatively satisfactory, and shape is not the only factor that influences user preferences for haptic feedback. To illustrate, as illustrated earlier in the graph that I showed, there's a strong preference for using 2D shapes for 2D objects and 3D shapes for 3D objects. We also calculated agreement scores for the broader categories of 3D shapes and 2D shapes, with all of the virtual objects receiving a score of 1 except for 2, which were the flashlight that received a score of 0.9, and the pen, which received a score of 0.605. We also note that participants, for the most part, appeared to mimic virtual objects' physical shapes. Through participants' approximations of shapes, we saw positive goodness in E-scores, suggesting HaptoBend's simple design was still effective for haptic feedback. This further supports the effects of visual dominance. While mapping shape F to the pen, one participant voiced this effect well by saying, even the lack of roundness doesn't really matter. What matters more is that it feels like I'm holding some sort of elongated barrel shape in my hand. Overall, participants tolerated perceived weight differences between HaptoBend and virtual objects well. However, the lightest and heaviest objects did show some issues. The pen received 6 negative mentions related to weight differences, while the sledgehammer received 2 positive and 2 negative. The perceived function of some virtual objects had an effect as well on the participants' preferences. For the notebook, most participants folded the device in half to create the ability to open and close a book instead of choosing shape A, which was actually more similar in terms of size and shape. The smartphone shows another example of this. Many chose shapes A and B, which are flat but also larger than the smartphone, instead of dimensionally similar shapes that were not completely flat. One reason for this was to maintain a flat surface needed to interact with the touchscreen. To explain the inability of the hinges to fold completely flat in more detail, we can see here that the bend angle was limited by the material used to construct the prototype. This affected how flat shapes C and D could be. Differences in size were tolerated well by participants for all shapes but the pen. This caused 4 participants to use HaptoBend in shape B to mimic the pen's thickness. To do this, they held HaptoBend by the edge and used the corner as the pen tip. Here we can see HaptoBend held in this manner. The factors of shape, weight, size, and function contributed to each of the most preferred shapes for each virtual object. For the smartphone, the most preferred was shape B. For the notebook, the most preferred shape was shape C. For the tablet, it was shape A. For the pen, it was shape F. For the flashlight, shape E saw the most use. And for the sledgehammer, E was also the most prominent. We see a lot of potential in continuing shape-changing interfaces in virtual reality as a research topic. The effects on tolerances for disparities in shape, weight, size, and functionality need to be explored more. And also using shape-changing devices for task completion in VR needs to be done to understand how effective they are. Also, there's a number of design improvements that we observed from feedback from users during the user study. These include providing more shape options, hinges that allow 180 or even 360 degree rotation, being able to lock the device into different shapes, minimizing the wire connections so that they don't conflict with different hand positions, and also adding translation tracking. I'd like to thank my co-authors to the paper, Audrey Girouard and Robert Teather, who both contributed a lot to the research and writing of the paper. And I'd like to thank you for listening to the presentation and also invite you to come to our demo, which will be up during demo sessions. I'll now take questions from the audience.
So we have a little bit of time. Any questions? I think everybody wants to go.
It's been a long day, it's fine.
I really like this object because now it seems pretty simple, but I imagine it a collection of a wireless, a bunch of those on the table, and the possibility to create shapes much more complex than this. So maybe there will be other sensors similar to that with other shapes, with the carved curvature surfaces and so. So I think, do you have this in mind, so to scale up?
Yeah, so I'd like to continue this research for my thesis and kind of integrate as many of the design improvements as I can into it. I think that there will probably be limits to what I can do with one prototype in the next iteration, but looking at things like being able to actuate into different shapes, being able to maintain the shapes by locking into place, and especially translation tracking. I think these are all really additive things. Then those all kind of have to be balanced with things like how many wires you want to come out and how that affects hand positioning. So I kind of see a couple different directions that you could go in this, and I think that they're combining the fields of shape change and VR haptics. There's a lot of opportunity there because it hasn't seen very much kind of crosstalk so far.
So just, I think the haptic word is a little bit overused in this application, because I suppose there is a kind of resistance from the controlled resistance, a kind of force. Probably I suggest to switch to tactical interface.
Tangible?
Yeah, because probably it's more suitable. Thanks.
It's just a comment more than a question. There's these little robots you can buy that magnetically snap together.
Yeah.
And this reminds me a lot of that, but I could see a lot of benefit of going that route where you could form sort of arbitrary shapes from blocks on the table, but also each of them have actuators potentially. And so I can't remember the name at the moment, but if you just search for cube robot, I'm sure you'll find it.
Yeah, definitely. Thank you.
All right. Thank you, everyone.